What if we have one of our limits on our integrals is infinity, or what if, remember back when we did integrals, so what if it's, what if it's an infinity, one of the limits is infinity? 1 to infinity, 1 over x squared dx. Well, in the first place, does that even make sense? And it does. In certain cases, it actually is we can compute it. But yeah, we can have an infinite limit, and that actually turned out to be a number. And we'll look at that a little bit in a little bit here. But here's another one. This is the one I got written down here, so I'll go with it. All right. Now the problem on that one is, that doesn't have an infinite limit. The problem on that one is, do you notice here 0 to 2, what is included in 0 to 2? 1 is included in 0 to 2, and what's wrong with 1? 1 makes that expression right there undefined. We can't substitute, we can't have a value of 1 there. And so we kind of encountered one of those, some of those like that in Calc 1. But what we said was, hey, we can't evaluate that because you got an undefined value there. Well, today's the day that we get to talk about what do we do in cases like that. These two are examples. This is an improper integral, and this is also what is called an improper integral for a different reason. This is an improper integral because it has an infinite limit. This is an improper integral because it has we call it a discontinuity. In the limits of integration, we have a discontinuity in the function here. So that's the two types of, this is type 1 we'll do, and this will be type 2. The two types of improper integrals that we have. Infinite limits and this is a discontinuity. Integral with a discontinuity. So we're going to talk about both of those types here as we go along today. We'll start with the infinite limit. And we'll start, matter of fact, we're going to start with the one I have right there, I believe. 1 to infinity, 1 over x squared. Yeah. Well, just think about what that really means. What we're finding here. What does an integral, what's the interpretation of it? Geometric, the graphical interpretation. It's the area under the curve. And in this case, we're talking about, so 1 over x squared, this piece would be the one, there's another piece over here. This is the piece we're interested in because we're going from 1 to infinity. So it's starting at 1, it's going out forever. That's what we're talking about here. So let's do this here. Let's evaluate. Let's go 1 to 5. See what happens there. Well, 1 to 5, 1 over x squared, of course, that's just power rule. X to the minus 2, right? So power rule will be negative x to the minus 1. And we're going 1 to 5. So basically, we've got negative, 1/5 minus a negative 1, which is 4/5. 0.8, however you want to write it. 4/5, probably your best way. All right, now let's bump it out. Let's go a little further out, 1 to 10. So 1 to 10, 1 over x squared dx. We have the same integral here, same antiderivative. We're going 1 to 10, so You plug in the 10 to the negative 1, so it'll be negative 110 minus, plug in the 1, you still get negative 1. That makes a plus, so you got negative 1. That's 9/10. Okay? Well, let's go way out there. Let's bump it up to 100. Integral 1 to 100. So we're getting, I mean, we're not close to infinity, but we're getting further out there. 1 to 100 of 1 over x squared dx. Well, same old, right? Antiderivative is negative x to the negative 1. Plug in the 100, you'll have negative 100 to the negative 1 power, so that'd be negative 100, right? Minus, plug in the 1, you got minus 1. Well, guess what? Minus makes a plus, you got 99 of 100. Well, a couple of things that this shows us. It does seem like, you know, that's 4/5, 0.8, that's 0.9, that's 0.99. Does this remind you of anything? It's kind of a limit thing? Yeah. As we're progressing here, it looks like as my top limit gets larger and larger, the values of the integral are getting closer and closer to 1, yeah. So these are closer and closer to 1. So we've got a limit thing going on here. And that's how we're going to do these improper integrals, is we're going to use limits. I call it, maybe the book calls it too, T-limit. But here's how this works. How do we prove that is the case? I mean, that's pretty good evidence. If we do 1,000, I think it'd be fairly easy to see that that's 999 out of 1,000. Well, how can we do it more directly, I guess? Or we're going to use limits. Here's what we do. So we've got this integral, 1 over x squared dx. And so what I'm going to do is I'm going to replace, leave a little space here, I'm going to replace the infinity by a t. We're not going to use u, I guess, since we use u for u substitution. So they use t for this replacement here. And the way we're going to kind of get the infinity is I'm going to take the limit then as t goes to infinity, which is sort of what we were doing here, right? We were letting the t, the top value, go to infinity. So it's the same, kind of the same idea, except writing it more directly here. So we're going to change this to this limit here. Limit as t goes to infinity, and that's because the t has replaced the infinity, if you will. All right, well, it's really, you do the limit kind of at the very end. That the process here is the same as, you know, you got to do the antiderivative, however, parts, u substitution, you know, you're just going to do that antiderivative, so, you know, have to know that stuff too, and we've already done it. We know that the antiderivative here is negative x minus 1, but we're going to do that from 1 to t, and so that puts it at this. It'll be negative t to the minus 1 minus negative 1 to the minus 1. Okay. And probably, you know, when you get to these negative powers, it's probably a good idea to write them as positive powers. So we're going to change that. T to the negative 1 is 1 over t. Of course, this is plus 1. Do all that. With me so far? So far, so good? All right, now, once we get it where we got it simplified as we can, now we do our limit, which is, you know, the same as we've done limits before. Sometimes we might have to use L'Hopital, not very often, but we might have to use L'Hopital, or there's some other things that we'll talk about what happens here. But this one's pretty easy because I do the, you know, just make that substitution there. We know about that, don't we? 1 divided by an infinitely large number, a 0, isn't it? Yeah, 1 over infinity or negative 1 over infinity. Anything over infinity, number-wise, over infinity, that's 0. Ta-da. What we thought it was. Okay? So that is how we're going to attempt to do those. Now, a couple of points. First of all, with these improper integrals, sometimes, we may not get a number, we may get infinity. You may get an answer for an integral to be infinity or negative infinity, or it may not be a number. But if we do get a number, a fixed number, we say then for these type of integrals, they converge. Okay, so this integral, since I've got a fixed number here, since the answer was a fixed number, or a number, not infinity or undefined or something like that, the integral 1 to infinity 1 over x squared dx is said to converge. I don't think we've used that term before in our discussions, but yeah, we're going to use the converge, and then if it does the infinity or does not exist thing, diverge. It diverges. So this one, since it goes to a number, converges. And then the other thing to point out is, again, this graph, the area under the curve, the area is 1, from 1 to infinity. So even though this doesn't ever stop, the area under the curve is 1. So kind of sort of a strange deal. Any questions on that? Well, all right. Try another one. What about 1 to infinity x e to the minus x squared dx? So again, t replaces the infinity, and then we say limit as t goes to infinity, 1 to t x e to the minus x squared dx. Well, how shall we do the antiderivative there? How are we going to figure this integral out? Yeah, it's a u substitution, isn't it? That's always the first one we look for. This is a u substitution. U replaces what? The power, right? The minus x squared. And then du, don't forget you got to do the du here, so it's minus 2x dx. And so du over minus 2x is what I replace my dx by. So limit as t goes to infinity. And these are x values 1 to t. I am making the u substitution. Minus x squared u. Du is du over minus 2x. Yeah, so I've got a minus 1/2 e to the u. Yeah, these are x values. So we change them over to u's, but I don't think we want to do that. Yeah, so minus 1/2 e to the u. That's an easy one, isn't it? What's the antiderivative of minus 1/2 e to the u? Minus 1/2 e to the u. Okay. But the u is, let's go ahead and change that back to minus x squared. And then that's going to go from 1 to t. All right, so we plug in the t, we'll have minus 1/2 e to the minus t squared minus a negative 1/2 e to the minus 1. If I do the 1, it's minus 1 there, right? Because I'm just squaring the 1, then I negate it. So again, my recommendation usually, if we have a minus power, flip it over. So let's make that adjustment there. So it's minus 1 over 2 e to the t squared. Because the minus t flips over, gets knocked into the denominator there. Then this makes a plus. I guess we can do the same thing there. It's 1 over 2e then. E to the first. It's just e. Okay? Yes? All right. Now we can go and evaluate our limit. If I plug in the infinity there, well, it's infinity squared, so I have 2 times e to the infinity. What's that going to be? Minus 1 over 2 e to the infinity squared. What's that, isn't it? Infinity squared. E to the infinity squared is infinity, all right?
Yeah.
E just keeps, if you do powers of e, that's just going to keep growing and growing. So e to the infinity squared is just infinity. So what's going to happen to this term right here?
0.
That's going to be 0, yeah. 1, again, divided by, or negative 1 divided by a larger and larger number, that's still 0. So 1 over 2e converges. Again, that's just a term we use for ones that go to a specific number. Is that okay? All right. Well, they don't always go to a number. Let's look at this one. What about 2 to infinity, 1 over x dx? All right, so we'll do our limit as t goes to infinity again. So it'll be 2 to t now, 1 over x dx. Well, we like when we come across those integrals. I mean, if we know them, we like when we come across them. That's an easy integral, right? 1 over x. What is it? Ln absolute value of x, okay. Now we're going 2 to t. So it'll be the limit as t goes to infinity. Plug in t, so it'll be ln of absolute value of t minus the ln of absolute value of 2. So we wind up with, so t goes to infinity, so this is ln of infinity minus ln of 2. Absolute value of 2 is 2. What you got there? What's the ln of infinity?
Infinity.
That's infinity, isn't it? Why? You're taking the ln of a larger and larger number. Well, one thing I always say if you're kind of iffy on what happens here is look at the graph, right? If you look at the graph of y equals ln of x, as x goes out to infinity, that thing is not leveling off. There's some, we'll talk about one here in a second where it levels off as you go out to infinity, but not ln, it just keeps going. I mean, it's gradual, but it does get larger and larger. So yeah, this is infinity minus the natural log of 2. This is probably not the most accurate thing I could write up here, but visual, it's visual. All right, so that's infinity minus a number. What's infinity minus a number?
Infinity.
It's still infinity, yeah. Yeah, this one, you can't actually compute, where it grows larger and larger and larger. It's a larger and larger number. So this one diverges. If it does something like that, your integral is said to be divergent. Just note that, because I think they will ask you about converging. Does it converge or diverge? Well, if it goes to infinity, it diverges, or negative infinity. But that's kind of interesting too. If you look at, remember a while ago we looked at 1 over x squared to infinity, 1 to infinity I think it was, and it converged to 1. It converged to 1. This is just 1 over x. That's kind of close to what 1 over x squared is. If you think about the graph, it's very similar, graphically speaking. But, and this, we started at 2, I don't know why I started at 2. Oh, I think I did, so I have that number there. But that's real similar to the graph of 1 over x squared, isn't it? Which is 1 over x squared, that area is 1. What's this area? It's infinitely large.
Yeah.
Kind of strange, huh? Kind of weird, but that's the way it works. Okay. So here's another one. Let's see how this one goes. So say we got integral negative infinity to 2 e to the x dx. Yeah, because not only can you do this with infinity, the top limit, but we can also do this with infinity as the negative infinity as the lower limit. That's the same concept. Going to do the same thing. So in this case, t goes in for the negative infinity, so my limit is t goes to negative infinity. So that does change. There's t here, 2 there, e dx dx. Well, again, we like the ones where I usually don't give you those on the test, though, do I? Those easy ones.
Yeah.
Sorry. There it goes. So it's e dx. It's e dx. E to 2. So that's e squared minus e to the t. So t is going to negative infinity, so we've got e squared minus e to the negative infinity. I guess there's a couple ways you can think of that. Again, it's got a negative power, so that's the same as, wouldn't that be the same as 1 over e to the infinity? Which what does that do?
0.
That's 0. So e to the negative infinity, 1 over e to infinity, goes to 0. So this is e squared. Convergence. All right. Okay. I mentioned a while ago when we were talking about, here it is, ln of x. That just keeps creeping upward and upward. Well, one of the graphs or functions that levels off at a specific number is the inverse tangent. Remember talking about that in trig maybe? The graph of inverse tangent, not tangent, the graph of inverse tangent. Kind of resembles this. Sort of has the same, but it's different in that this, we've got a horizontal asymptote. This levels off, in other words, out here this way. Remember what this number is, where it levels off? It's the same as the vertical asymptote of tangent. Remember when you do tangent, you've got those vertical asymptotes. And so this horizontal asymptote is the same as that vertical asymptote. Pi over 2, yeah. And then it levels off back this way, negative pi over 2, yes. Well, why do I mention that? Because if I do the limit as x approaches infinity of tangent inverse, what does that do? What's the limit, that limit? Pi over 2. And if it was negative infinity, it'd be negative pi over 2. Okay. So keep that one might come up. It comes up now too, but it might come up later on too. But we're also going to question.
Sounds like a test question.
Sounds like a test question. I did say it'd be on the test. It will probably be on homework, but I could throw it on the test. I think I have before, but it's not on all of them. So, all right, but let's also look at this. Can we do that? Sure, we can do that. Well, problem is, well, here's what we do. Best way to go about this is break it up into two pieces. And we've done that some before. Remember, I think it was the absolute value ones back in Calculus 1. We split it up at a certain point. Here we're going to split this up into two intervals. And, make it easy on yourself. We can split it up at any number we want. Let's just go with 0. What do you think? All right, so we'll go negative infinity to 0, and then 0 to infinity. So we're covering the whole space there, the whole limit there, but for all the limits. But break it up because, yeah, we're going to have to let t go to, in this case, let t go to negative infinity and then let t go to positive infinity here because that may make a difference on our limits. One may converge and the other may not, or vice versa. All right, so yeah, on the first one then, t, it's the limit as t goes to negative infinity. T's down there. And then on this one, it's the limit as t goes to positive infinity. Which brings up why I've just talked about tangent inverse, because what is this? It's just tangent inverse, isn't it? It's a limit as t goes to infinity, negative infinity, sorry. That's tangent inverse, just a direct antiderivative. T to 0, so on both of them it's tangent inverse. All right, well, let's plug in. So we got limit as t goes to negative infinity, tangent inverse of 0 minus tangent inverse of t plus, this will be the limit as t goes to infinity, tangent inverse of t first, then minus tangent inverse of 0. But what's tangent inverse of 0? 0. That's 0. So we just wind up with our negative tangent inverse of t. And then over here we'll have the limit as t goes to infinity. Tangent inverse of t. Yeah, because this is 0. That's 0. Yeah, so we got, well, look at that. So we got both. T goes to negative infinity, tangent inverse, negative tangent inverse, t goes to infinity, tangent inverse. However, this is negative tangent inverse of t. This right here is t goes to negative infinity. That part goes to negative pi over 2, doesn't it? But we've got the negative here, so we've got negative pi over 2, right? Plus t goes to infinity, well that goes to pi over 2, positive pi over 2. So what do we got? Pi over 2 plus pi over 2. Pi. That's pi. Okay. Good on that?